So here is something that looks familiar from your math career in the past. You were given something like this, and it said, find x, right? Find x, or solve for x. So the way we want to think about this, when you look at this, is we can let x be many different values, okay? So we could let x be 0. What happens when we let x be 0? What's the consequence of that? If x is 0, what happens? What's that? It's not true, right? It says, the statement says no, it's a false statement. What about when x is 1? Does it work? Nope. When x is 1, we get negative 1. It's trying to say negative 1 equals 5. So it's perfectly legitimate to say x equals 1, but then we just have to say, well, x equals 1 doesn't make that true. Okay, and then you learned algebra in order to find particular values of x that made it true, right? That's what you were doing. You were finding which values of x make this statement true. That's a typical equation. In this case, only 2 values of x will satisfy or make that equation true. All the rest render it a false statement. Okay, well, what about this? What about when x equals 0 here? Does it work? X equals 0. We get negative 1 on the left. And what about on the right? Negative 2 times 1 times 1/2. Negative 1. It works, right? What about when x equals 1? Oh, sorry. Is that what I just did? I just did that. So x equals 0 works, and x equals 1 works. All right? And in fact, what happens here is it doesn't matter what x value you put in. You can put in 100, you can put in 1,000, you can put in negative 50, you can put in pi, you can put in negative 2/5, and it will always make that statement true. So x can take on many values, and here every value of x makes the equation true, no matter what x you put in. So do you see the difference between the two? Only some x's work, all x's make it true. So that's what we call, the one on the right is what we call an identity. Identity. No matter what values of x you put in, it always is true. And this is very applicable in trig because we have these different relationships that are all intertwined. And so that results in many, many identities. Many, many identities when we're talking about sine and cosine and tangent and then other relationships that we'll talk about. You have all these intertwined relationships that result in lots and lots of identities, and then those identities are helpful in solving problems. Okay? So you're doing some algebraic work, and say you have something like this, and then it helps then to use this instead. Okay? Because they're always equal, no matter what x is. Okay, so we're going to build some of these based on our knowledge of Module 7. Okay, read carefully and slowly. This is all. Everything that you do on this is all based on this Module 7 that we just got done with, and you all did pretty well, or as a group, we did pretty well on the exam. So let's start with the first one. Suppose the circle has any radius. Okay, it could be half a centimeter. It could be 70 miles. Okay, the radius. Using radius lengths as the unit of measure. Okay, so not the units of the radius, not miles or inches or feet, but using radius lengths. I want you to label the 3 sides in terms of their side lengths of that right triangle that you see there at right. Okay? So if we got the main ideas from Module 7, we should be able to label the 3 sides of that triangle in terms of theta. And in terms of radius lengths. Okay, I want you to get someone to work with on this. So either groups of 2 or 3. Groups of 2 or 3. No bigger than 3. How many radius lengths is the hypotenuse of that triangle? It's 1, right? 1 radius length. And then to this point, defined by theta, this is simply the horizontal distance to the right of the vertical diameter. And if I want it in radius lengths, that is cosine theta. And then this is the vertical distance above the horizontal diameter. In radius lengths, that is sine. Okay, so the question is, if I change theta, does it, and then you notice that's a right triangle, and so if you want to square the output of sine, you put the square right after sine, not after theta. If you put the square after theta without parentheses, that indicates to square theta, and then put it into sine. That's not what we want. We want to take the sine, we want to get that length, that's our output, and square it, and that's how you show that. Okay? So the question is this just an equation, or is it an identity? And how do we know? Is it just an equation that works for some theta and doesn't work for other theta? Or is it an identity? Does it work for all theta? So I can change that triangle. So what about this triangle? I'm going to get it. There we go. Does it work for this triangle? I just changed theta. Will it work for this? Yeah, because this right triangle is always maintained, where cosine theta is this horizontal distance, sine theta is the height of the triangle, and that hypotenuse is always 1. So this is an identity. In fact, this is probably the most common identity you'll see in your math and science and engineering career. Okay, it comes up all the time. It's called the Pythagorean identity because it's based on this right triangle and the Pythagorean theorem. Okay, questions on that one? So using side lengths in that triangle, how can we write tangent theta? Okay. Yeah, so remember the one meaning we had was the slope of the terminal side, right? The slope of the terminal side. This purple line right here is the terminal side of theta. The slope of that was one meaning of the output of tangent. And so to get slope, we would take how much we go up for every amount that we go over, right? So is that true for all theta? Is it an identity or just true for some theta? All theta. So it doesn't matter what we choose for theta or what you plug into that, it's always going to make it true. Because the slope of that pink line will always be the light gray line length divided by the black line length, sine over cosine. Okay, where do we go from there? Were we doing the shifts? Is that the next one?
Yes, 3 is about the cosine and shifts.
Okay, so I won't go into it in detail, but if you're lagging behind cosine by pi over 2, then what's the argument? The new angle argument is plus or minus pi over 2. Yeah, lagging behind. So that argument angle is lagging behind. It's behind. And did you draw that to the right? Is lagging behind to the right or to the left? Coming later. Coming later. To the right, right? Its cycle comes later, so it's to the right. And then if you drew that whole thing, you should have noticed, oh, that looks familiar, like something else besides cosine. What does it look like? It's sine. Did you see that when you drew cosine of theta minus pi over 2, you should have been drawing just the plain old sine curve. So there's another identity. And then on the next page, we want to draw sine, but for an angle that's ahead by pi over 2. So is that plus or minus? And then did you draw that shifted to the left or to the right? So if it's ahead, it comes first. So is it left or right? Left. It's coming. Its cycle starts first. It's ahead of. And then when you drew that, you should have noticed that you get cosine. Question. So I'm not going to go through those. Just talk through them. So questions about those two? So we're building a toolbox of identities that when you get to problems dealing with right triangles and other trigonometry and other circles, you have these relationships that help you solve problems. Okay? All right, let's talk about the next one. So it first asks the meaning of, if theta is our standard angle that we've been talking about for a month now, what is the meaning of the opposite of theta? Nadine? What's the meaning of the opposite of theta? Any idea? What's that? It's the same. The opposite of theta is the same angle as theta. Is that what okay, so how would we define the opposite of theta? What would we? Not inverse. Jaden. She said the measure of the angle swept clockwise from the 3 o'clock position. That's exactly what the opposite of theta would be. If the opposite of theta would be then this angle swept clockwise. So now what we're interested in, so that's the green angle on the screen. In the back row, can you guys see the green? So we're interested in, you can't see it?
Yeah, never mind. Yeah.
Can you see it? All right, let me change it. Let's try blue. Okay, we'll do blue. So now we want to talk about the sign of the opposite. So here's this angle swept clockwise. Swept clockwise from 3 o'clock. How does the sign of that angle relate to the sign of our angle swept counterclockwise, our traditional? So we want to come up with a relationship between these two. How are these related? The sign of our standard angle and the sign of our clockwise swept angle. So anybody have any idea? So I can give you a visual here. So you're comparing the sign of the purple angle and the sign of the blue angle. Taz, Christian.
They're both the same value, but one's negative and one's positive.
Okay, what were we going to say, Taz? Okay, so he said one is positive and one is negative, and he said that sine of opposite of theta is the opposite of sine of theta. What do you think? What is the meaning of sine of theta again? All right, so do you see in this picture that I'm showing you here, do you see what's representing sine of theta? Fuda, what is representing sine of theta in this picture? This one? Yeah. Good, okay. So this right here is sine theta. And right now, is it positive or negative? Okay, what in this picture is representing sine of the opposite of theta? Patrick? This one here. So Christian and Taz both said these are equal and opposite values. Jane, you agree with that? These are equal and opposite values. Sine of theta, which is that distance, and sine of opposite theta. Yeah, sure, maybe. What do you think? Yeah, that's what it is. And what about if we get into the second quadrant with our theta, and that makes third quadrant? Does it still hold? Sine of theta, positive or negative? Sine of the opposite of theta, positive or negative? That's negative, so equal and opposite values. So what identity can we write then? Sine of the opposite of theta equals? Opposite sine of theta. And as you see, as I change that angle theta, you can see that it holds true for all angles. No matter what angle I pick, those are always going to be equal and opposite quantities. All right, what about cosine of the opposite of theta? So where in this picture right now is cosine of theta represented? Jared, can you see in this picture, can you describe to me where cosine of theta is represented? Distance to the right of the vertical diameter. So starting where along here? Here? Like that? Right there. That's my cosine of theta. What about my cosine of the opposite of theta? Hamid?
From 0 to the left side.
0 to the left. Like this?
Yes.
Is this showing cosine of theta? Opposite of theta? Here's the opposite of theta, right? So here's my point. So how is the cosine of this angle represented? Here's the point. Here's the terminal point. Yeah, Christian.
By the same line, the same black line.
Yeah, it's the same. So do you see this is the same line? So the horizontal distance to the right of the vertical diameter is the same at this point and at this point. It's that black line right there. Is that true for all angles? Oh. So the 2 points, the terminal points of our angles, is the cosine the same whether you do the positive angle or the negative angle? Is the cosine the same? Yeah, you see it's this right here. Whether we go positive or counterclockwise or if we go clockwise. All right, so write the identity. What would it be? Walter. Cosine of negative theta equals what? Cosine theta. Diana, you agree? Yeah, no matter what angle you put in, if you go clockwise or counterclockwise, your horizontal position is the same in both cases. And that's what that's saying. Whether you go clockwise or counterclockwise, you always end up at the same horizontal position on the circle.
It's just that the value of sine is different.
And how is it different? How is sine different?
Because sine is measuring vertical.
Okay.
distance instead
Because it's measuring vertical distance, then how are they different?
of, because when you actually.
No, how are they different, not why.
Oh, how is what different? Like cosine?
Sine. You're talking about sine. How is the sine of theta different from the sine of the opposite of theta?
Because it's a bounce from the front.
But what's the relationship? How are they different? Is it 3 times? Is it 3 times? Is it 100 times? Is it plus 10? Or?
They're one.
Hey, they're 1 to 1, but you're telling me they're not the same. 1 to 1 is the same.
Sine is not the same. The plus and negative.
Right.
Okay.
They're equal magnitude, but they're opposite each other. One is negative 1 times the other. Yes, that's how they're related. Okay, so then the last one is kind of a cool derivation of 1. Let's see if it's still up here. Okay, so this is angle elevation 1.2. Okay. I want it bigger, not smaller. How do I do that? There we go. Okay. So there's 2 triangles here. So here's my standard angle. The pink one is the standard angle. Okay, so I'm showing that. And then I'm showing the opposite of, or the clockwise version, green there. I'll do black. Shoot. Not. There we go. I'm back. All right. So the pink is our standard angle swept counterclockwise from 3 o'clock. This black one is the opposite of theta, right? That's the clockwise version. Okay? And then, starting at this pink line, we sweep another theta. Okay, so starting from the pink line, sweep another theta. So I'm going to draw 2 triangles. The blue one is there, and I'm going to draw a new triangle that's red. Okay? So this triangle right here. From there, down like that, and then down like this. I'll make a little bolder here. So you have 2 triangles that you're looking at. And what we're going to do is we're going to calculate the area using our trig understanding of trig. We're going to calculate the area of each of those 2, the red and the blue. So do the blue first, and then do the area. So in order to do that, we need to know the area of a triangle, just in general. What's our area formula for a triangle? Area equals? Not base times height. 1/2 base times height. So you're going to do that twice. Using your trig, you're going to find the base and the height of the blue triangle and the base and the height of the red triangle. Okay, so this takes a little investigation. It takes a little, critical thinking to do it. But you've got all the tools you need in your trig functions. Okay, so what's the area of the blue triangle? Meaning, what's the base of it? What's the height of it? And what's for the red triangle? Same thing. All right, go. The blue triangle goes all the way up to the right side of the 3 o'clock position. It goes all the way to the 3 o'clock position. Okay? Goes all the way to there. Red first. So, yeah, nice. What? The third one, actually. Yeah. The base with Go. The blue. No R's. All in radius lengths. Everything in radius lengths. No R. So that's a great idea. So in radius lengths, what is that? How many radius? 1. Yeah. Everything in radius lengths. Again, doesn't matter how big the circle is. Measure everything in radius lengths. Yeah. And then the other one is good. Yeah. Good. Oh yeah, that's a great picture. No, what's it reading? So what's the base? What's the height? Base is 1. Got it, you got the tool for it. So we'll do it. This angle 2 theta, right? What you want? Switching up 2 theta, and what do you want? Well, let's put that 2 theta. Vertical distance above the horizontal diameter. Two sides. Angle is 2 theta. What you want relative to that angle. Here's your angle. See? Here's your angle. It's 2 theta.
I think
This right here.
the base is 1.
This is the vertical distance of the horizontal diameter.
Yeah. I just think it's cosine negative theta.
The blue one is actually easier to get the base. The base, the radius. The height of this is sine of sine of theta.
Let's make sure. The blue one is sine theta, sine 1.
You started here and you went all the way here. So how many thetas did you go?
What's the base of the blue triangle in radius lengths? Isn't that the radius, right? The base of the blue triangle is just the radius. It's 1. Are we good? Does that make sense? What's the height of the blue triangle? So, have you learned something? What's the height of the blue triangle? It's a sine, right? Because it's a vertical height to the circle. Of what angle? 2 theta. Swept counterclockwise from 3 o'clock is 2 theta to get to that point. No, the height is the vertical distance above the horizontal diameter to the point on the circle. That's exactly what sine is, right? Sorry to interrupt. There's the blue triangle, 1/2, 1 times sine 2 theta. Okay, how did the red triangle go? Anna, did you get it? So what was 2 sine theta? Why 2 sine theta? So here's theta, so 1 sine theta would be here. And so 2 sine theta, so you're saying your base is this right side of the triangle. Good strategy, okay? So this right here, we can call the base, and that's actually 2 times the sine of theta. Do you see it? It's twice the length of the sine. Okay, and then what about the height? Why? Why is that the height cosine from where to where? From the base to the center. What does cosine measure? What is the meaning of that? Horizontal distance from vertical diameter. So where does that take us to? Right there. Because that would be our cosine. From there to there would be the cosine for that angle that gets us to that point. It's the x-coordinate of that point, right? It's the x-coordinate of that point. Okay, so notice that, remember your geometry? Remember your proofs, geometry proofs? What do you notice about these 2 triangles? How are they? Well, so triangles are congruent, right? Congruent. How are they congruent? Remember by what? How do we know that these triangles are really the same triangle, just in different positions?
Sides and
Yeah, okay. Remember your geometry proofs? So this Really, this side length is how long here? 1. How long is that? 1. And between them, how many? What angle? 2 theta. So we got side of 1, an angle of 2 theta, and a side of 1. If a triangle has that pattern, it's the same triangle. So if any triangle that has a side and then an angle and the side, it's the same, then the triangles are the same. So the red one, how long is it? 1, angle, 2 theta, length. They're the same triangle. This is called the side, angle, side. Side, angle, side. Remember that? Side, angle, side. 1, 2 theta, and 1 is the same in both triangles. So therefore, their areas, if they're congruent triangles, their areas are equal. So we're going to create an identity by setting these two equal. When we set those two equal, we can just multiply by 2 and get rid of the 1/2. And we get what's called the double angle identity. Sine of 2 theta, that's from the blue triangle, equals 2 sine theta cosine theta. Did you catch it? Did you see what happened? So we set up these two triangles that are really the same triangle, but oriented differently. And then from the blue one, we got sine 2 theta, and from the red one, we got 2 sine cosine theta. So that's an identity. That's true for all angles theta. Any questions on that process? Lots of people looking at computer screens. Are you looking at this problem? Okay. It's a good way to get called on. Keep looking at your computer screen. All right. So let's summarize what we learned here. Don't write all these down. It'll be on the video, and you can write it down later. Just check the video. Okay? So here's the first one we did, the Pythagorean identity, really important. Sine squared of the angle plus cosine squared of the angle equals 1. Comes from the right triangle. We did a couple shift identities. There's lots more that we could do. So this is just a couple examples of how we can get identities by shifting. Sine is like cosine, just shifted. All right, then we did these opposite angle identities. Here's this double angle identity we just did. For cosine, there's actually 3 versions of the double angle identity. We didn't show any of these. We're not going to take time to do every single thing. So I'm just going to give those to you. Cosine squared minus sine squared, 1 minus 2 sine squared, 2 cosine squared minus 1. Those are all the same. Those are all equal to cosine of 2x. So those are a double angle. Okay, so for the right triangles, remember we have the sine, cosine, and tangent. We've done those before. But with 3 sides of a triangle, you can actually make a total of 6 ratios. Okay? There's 6 different ways to create a ratio out of 3 sides of a triangle. So there's 3 more that we haven't talked about. The first one is, if you take the sine ratio opposite over hypotenuse and you flip it over, hypotenuse over opposite is what's called cosecant. And it's abbreviated CSC. So since it's sine, the sine ratio flipped over on its head, it's just 1 over, so there's another identity. The cosecant is 1 over sine because it's hypotenuse over opposite instead of opposite over hypotenuse. Okay? Red. Cosine. So we can take cosine, we can flip it over and do hypotenuse over adjacent, and that's called the secant function. So since it's just cosine flipped over, its secant is 1 over cosine. There's another identity. And finally, tangent. If you take tangent and instead of opposite over adjacent, make adjacent over opposite, that's the cotangent function. And since it's the reciprocal of tangent, it's also cosine over sine and 1 over tangent. and we know the tangent is sine over cosine. So this becomes a matter of memorization, okay? Having these at your disposal so that it helps you to solve problems, okay? Questions on. So now for the right triangles, there's actually 6 ratios. The 3 that we've learned, and then the reciprocals of those 3. So cosecant is 1 over sine, so it's hypotenuse over opposite. Secant is hypotenuse over adjacent, so that's 1 over the cosine. And then cotangent is adjacent over opposite, so it's cosine over sine or 1 over tangent. All right, so quickly, let's do one example here of any questions on that list. That's a pretty good starting list of identities. Like some of these are the most important ones you'll see. There are lots more. There are lots and lots more. Okay, so next day. In your book, you should have a page like this. I think this is at investigation mod 8, investigation 3. So what you have is these relationships of, what page is that on? 333? Look on page, I think it's 333. So what happens is you get these complicated expressions, and they can often be simplified into something much easier because there's all these relationships are intertwined, and there's so many kind of hovering around. Oftentimes there's complex relationships that simplify. Okay, and we see this in mathematics all the time. So that's what we're practicing here. So in doing that, here's the common technique is change everything into sines and cosines. That's one really important strategy. So for this first one, part A, we can start by changing cosecant, and what is cosecant equal to? 1 over sine. Okay? And what is secant equal to? 1 over cosine. So that's a first step. So we're trying to simplify this expression by using identities. Okay? So here's the first use. And then now, how does this simplify? So we can invert and multiply, right? When you divide by a fraction, you can invert and multiply. And what is this equal to? Sine squared. And what is this equal to? Cosine squared. So that's equal, and that's equal. And then what's that equal to? For all angles, right? We saw that. This is Pythagorean identity. For all angles, that equals 1. Therefore, that thing right there equals 1. So that's one important technique that helps with simplifying these expressions or these proofs, is get the whole expression in terms of just sines and cosines. And with the 6 trig ratios, you can do that. So you can rewrite all the cosecants and the secants and the cotangents in terms of sine and cosine and solve the whole thing, because most of our identities then are in sine and cosine. Okay? All right. So we'll have some homework practicing this kind of stuff for Thursday. Final exam is a week from tonight. I'll be posting a review soon. So, homework that we collected today. Spent a lot of the time answering questions on that. All the time if you need it. And if you have more time, you could have them work on B and C. How did your research little homework thing go? How was that? Well, were you collecting data with that or something? Or?
Well, we haven't gotten together.
Oh, okay.